Welcome to the deep dive, where we take a stack of information, pull out the key nuggets, and basically give you a shortcut to being well-informed. Today, we're diving deep into Group 15 of the periodic table. You might know it as the nitrogen group or the pnictogens.
That's right. And these elements, we're talking nitrogen, phosphorus, arsenic, antimony, and bismuth, they're incredibly diverse. I mean, essential for life, industry, but also, some pretty famous poisons in there too.
Definitely. So our mission today for you listening is to navigate this chapter from Shriver and Atkins Inorganic Chemistry. We want to cut through the complexity.
Exactly. We'll walk through the main ideas step by step. We'll try to explain the jargon in plain English, maybe describe some structures so you can picture them.
Sort of connect the dots, right? Think of it as your personal audio guide, no visuals needed to really get a handle on Group 15.
Yeah, we'll highlight the diversity, some surprising facts, and the basic chemical principles that show how these elements really shape our world.
All right, let's get into it. Section 15.1. The elements themselves, starting with nitrogen at the top, going down to bismuth, what stands out right away?
Well, the first thing is just the sheer range. I mean, nitrogen, it's a gas. Makes up, 78% of the air we breathe?
Right.
But all the others are solids under normal conditions. And it's not just a simple metallic trend downwards either.
Yeah.
Take phosphorus, for example. It exists in several different forms. Allotropes, we call them. Different structures, different properties.
Like carbon does with diamond and graphite, that kind of thing.
Precisely. So for phosphorus, you've got white phosphorus. It's this waxy solid made of little P4 molecules. Imagine 4 phosphorus atoms stuck together in a tiny pyramid, a tetrahedron.
Oh.
The bonds are really strained, like 60-degree angles, which makes it super reactive. It actually ignites spontaneously in air, forms P4O10.
Wow.
Then there's red phosphorus that's amorphous, less reactive, safer. And black phosphorus, which is the most stable form thermodynamically, it has these cool puckered layers.
Puckered layers. And arsenic, antimony, bismuth?
Well, arsenic also has different forms, like yellow one with azure tetrahedra, similar to white phosphorus, but also a more common metallic form. And metallic arsenic, antimony, and bismuth, they share a similar structure. It's like stacked, corrugated sheets, these puckered hexagonal layers. Each atom has 3 close neighbors in its layer and 3 more a bit further away in the next layer.
Got it. So lots of structural variety. And you mentioned something about conductivity being weird.
Yeah, it's a bit of an anomaly. Usually you'd expect conductivity to go up as you go down a group and things get more metallic, right?
Makes sense.
But here, it actually decreases from arsenic down to bismuth. It suggests that even though bismuth is, technically a metalloid bordering on metal, its solid structure still has a kind of molecular character.
Interesting. What else is notable about bismuth?
Well, a relatively recent discovery is that it's actually radioactive. It decays by alpha emission.
Really? Is it dangerous?
Not really, no. Its half-life is incredibly, unbelievably long, much, much longer than the age of the universe. So for all practical purposes, it's stable.
Phew, okay. And where do we actually find these elements naturally?
Nitrogen, obviously, is everywhere in the air. Phosphorus, that mainly comes from phosphate rock, things like fluorapatite or hydroxyapatite. They're basically fossilized remains of ancient sea creatures.
Like mineral deposits.
Exactly. And arsenic, antimony, bismuth, you usually find those in sulfide ores, often extracted as byproducts when mining other metals like copper or lead.
Okay, so that's the elements themselves. Now, how do they behave when they form compounds? What about their oxidation states? Section 15.2.
Right. This group shows a really wide range of oxidation states. It ties back to their valence electrons, the outermost ones. And a key idea, especially lower down, is the inert-pair effect. You might remember this from earlier chemistry.
Vaguely. Refresh my memory.
Sure. Basically, for the heavier elements like bismuth way down at the bottom, the 2 outermost electrons become kind of lazy. They're reluctant to get involved in bonding. And exactly, an inert pair. So while bismuth could technically reach a +5 oxidation state by using all its valence electrons, its +3 state, using only the p electrons, is much more stable.
Ah, okay. That explains why, as the text mentions, the -3 state is more stable for bismuth than +5. It holds on to those electrons.
Precisely. Now compare that to nitrogen at the top. It's completely different.
How so?
Nitrogen is super electronegative. Only oxygen, fluorine, and chlorine pull electrons harder. So it often ends up with negative oxidation states like -3 in ammonia, NH3, or in nitrites.
Nitrites, compounds with just nitrogen and another element.
Usually, yeah, like lithium nitride, L3N. Nitrogen only gets positive oxidation states when it's bonded to something even more electronegative, like oxygen or fluorine.
And its size matters too, right?
Absolutely. Nitrogen is small and doesn't have easily accessible d orbitals for bonding. So it typically forms only 4 bonds, max, in simple compounds. Heavier elements like phosphorus. They can easily manage 5 or 6 bonds, like in PCl5 or AsF6.
Okay, so nitrides. You
Yeah.
mentioned lithium nitride. Are there different types?
Yeah, the book classifies them into 3 main types. You've got saline nitrides like Li3N, or those from group 2 metals like Mg3N2. They notionally contain the N3 ion, but there's actually a lot of covalent character because that ion would be highly charged.
Makes sense.
Then, covalent nitrides, where the bonding is clearly shared electrons. Think boron nitride, Bn, or phosphorus nitride, P3N5.
Okay.
And finally, interstitial nitrides. These are formed with transition metals, the D block elements. Nitrogen atoms literally slot into the gaps, the interstices, in the metal's crystal lattice.
And what are they like?
Oh, they're tough.
Yeah.
Very hard, chemically inert, high melting points, metallic conductivity, great for refractory materials, things that withstand high temperatures.
Got it. And then there are azides. They sound different again.
They are. Azides contain the azide ion, which is N3. It's linear, 3 nitrogen atoms in a row with an overall negative charge. The average oxidation state of nitrogen here is weird. It's -13.
And their properties.
Well, they're generally toxic. And thermodynamically, they're unstable. They want to decompose. But crucially, they're often kinetically inert at room temperature. They need a trigger.
Like in airbags.
Exactly like in airbags.
Eh.
Sodium azide, NaN3, is the classic example. A small electrical spark makes it decompose incredibly rapidly, producing a huge amount of nitrogen gas. Like 50 grams makes 26 liters of N2, almost instantly.
Wow. That's explosive decomposition put to good use. What about phosphides and the others down the group?
Phosphorus forms loads of phosphides with metals. You have metal-rich ones, phosphorus-rich ones, lots of different structures with phosphorus atoms forming chains or cages. Metal-rich ones are often hard and conductive. Phosphorus-rich ones tend to be semiconductors.
And arsenides, antimonides.
Yeah, similar story. Particularly important are the arsenides and antimonides of group 13 elements, things like gallium arsenide, TRIAAs, or indium antimonide in DESP. They are vital semiconductors in electronics, LEDs, that sort of thing.
Okay, let's shift gears to oxides. Section 15.3 focuses on nitrogen oxides and oxoanions. It seems like nitrogen and oxygen make a lot of different compounds.
They really do. It's almost bewildering, honestly. It just shows nitrogen's versatility. You find NO compounds representing almost every oxidation state from +5 all the way down to METIC 1.
Let's start at the top, +5.
Okay, nitrogen V. The big one is nitric acid, HNO3. Huge industrial chemical. Its ion, the nitrate ion, NO3, is a decent oxidizing agent, though often a bit slow to react.
And this is where aqua regia comes in.
Exactly. Mix concentrated nitric acid with concentrated hydrochloric acid, and you get aqua regia royal water. It's famous because it can dissolve noble metals like gold and platinum.
How does it do that?
It's a combination. The nitric acid oxidizes the metal, and the hydrochloric acid provides chloride ions that form very stable complexes with the metal ions, like ACl4. That complex formation pulls the reaction forward, making the metal dissolve.
Clever chemistry. What about nitrogen one?
That's mainly nitrogen dioxide, NO2. It's a brown gas, and it's actually a radical, meaning it has an unpaired electron. It exists in equilibrium with its dimer, the nitrogen tetroxide, N2O4, which is colorless.
Ah, so that equilibrium explains why the color changes with temperature.
Precisely. Cool it down, the equilibrium shifts towards the colorless N2O4 dimer, and the brown color fades. Heat it up, more brown NO2 forms.
Got it. Nitrogen 3.
That gives us nitrous acid, HNO2. It's a relatively strong oxidizing agent. Its anhydride, dinitrogen trioxide, N2O3, is an interesting deep blue solid, but it readily dissociates into NO and NO2.
And nitrogen 2.
Nitric oxide, NO. Another radical, an odd electron molecule. Unlike NO2, it doesn't really dimerize in the gas phase. What's fascinating about NO is its biological role.
You mentioned that earlier.
Yeah, our bodies actually generate it. It acts as a signaling molecule involved in things like relaxing blood vessels to lower blood pressure, and also in neurotransmission. Pretty amazing for such a simple molecule.
It really is. Okay, last one, nitrogen.
That's dinitrogen oxide, N2O, also known as nitrous oxide.
Laughing gas.
The very same. It's a colorless, fairly unreactive gas. Historically used as a mild anesthetic, though less so now due to side effects. Its inertness actually led to its use as a propellant in whipped cream cans.
From dissolving gold to whipping cream, nitrogen oxides cover a lot of ground.
They certainly do.
Okay, let's move into Part B, digging a bit deeper. Section 15.4 talks about occurrence and recovery. We touched on this, but how do we get these elements on an industrial scale?
Right, the methods are quite specific. For nitrogen, it's huge scale. We just cool air down until it liquefies, then fractionally distill it. Liquid nitrogen is super useful as a refrigerant too, of course.
Simple enough. Phosphorus. You mentioned phosphate rock.
Yeah, historically it was first isolated from, well, you heard,
Curiously.
seriously. But today it's all from phosphate rock. Two main routes. One is brute force. Heat the rock with carbon and silica sand in an electric arc furnace to about 1500 degrees CO. Phosphorus vapor comes off, which you condense into that reactive white phosphorus P4.
Okay, intense. The other route.
Treat the apatite rock with sulfuric acid. This produces phosphoric acid, H3PO4, which is then mostly used to make phosphate foodalizers.
And the heavier ones. Arsenic, antimony, bismuth.
Arsenic often comes from the flue dust collected during copper or lead smelting. Or you can heat specific sulfide ores like arsenopyrite, VAS. Antimony is usually recovered from this sulfide ore, stibnite, Sp2S3. By heating it with iron, the iron grabs the sulfur. Bismuth is mostly a byproduct, recovered during the refining of other metals like lead or copper.
So quite different processes, which leads nicely into section 15.5, uses. We've hinted at many, but let's consolidate. Nitrogen.
Beyond the obvious biological necessity, its main uses stem from its inertness and its compounds. Huge amounts are used just as an inert atmosphere in chemical plants, food packaging, electronics.
To stop unwanted reactions.
Exactly. Then industrially, the Haber process for ammonia, NH3, is king. That ammonia goes into fertilizers, primarily, but also into making nitric acid via the Ostwald process, which then goes into explosives, plastics, dyes. It's fundamental.
And phosphorus.
Well, some elemental phosphorus is used in things like pyrotechnics, smoke bombs, even steel making. Red phosphorus is on the striking surface of matchboxes, but the vast majority is used as phosphates.
Fertilizers again, and detergents.
Yes, massive amounts for fertilizers. It's essential for plant growth. And sodium phosphates, especially condensed ones like sodium tripolyphosphate, were huge in detergents. As builders, they soften water by grabbing calcium and magnesium ions. And of course, biologically, phosphate is in our bones, teeth, DNA, RNA, and crucially in ATP, the molecule that carries energy in our cells.
Arsenic. Beyond its reputation.
Its main modern use is quite specific. As a dopant in semiconductors, particularly gallium arsenide, GAs, for high-speed circuits and lasers. It is toxic, but it's also actually an essential trace element for some animals, believe it or not.
Really?
Yep. And historically, arsenic compounds, arsenicals, were used as medicines for syphilis, sleeping sickness, and as pesticides and herbicides, much less common now, obviously. There's also the famous Marsh test for detecting arsenic, which produces the toxic gas arsane, AVH3.
Antimony.
Also used in semiconductors, especially for infrared detectors and LEDs. Its main bulk use is probably in alloys, particularly lead alloys, to make them harder than car batteries. Antimony oxide is also important. As a synergist, it boosts the effectiveness of flame retardants in plastics and textiles.
And finally, bismuth.
Well, bismuth B compounds are very strong oxidizing agents thanks to that inert-pair effect making BV unstable. Medicinally, you find bismuth subsalicate, the active ingredient in Pepto-Bismol, actually used for upset stomachs and ulcers. Bismuth 3 oxide is also used in some creams.
Pepto-Bismol. Okay, I didn't know that was bismuth. Let's talk about nitrogen activation, section 15.6. Nitrogen gas, N2, is everywhere but so unreactive. Why is that again?
It really comes down to that incredibly strong triple bond between the two nitrogen atoms. It takes a massive amount of energy to break it. Plus, chemically speaking, there's a large energy gap between its highest filled molecular orbital, H-HOMO, and lowest empty one, L-LIMOO, making electron transfer difficult. And it's not very polarizable either.
So it just doesn't want to react. How do we force it? The Haber process.
That's the industrial workhorse, yes, the Haber-Bosch process. Combining N2 and H2 over an iron catalyst at high temperature, around 450 degrees C, and very high pressure, maybe 100 atmospheres or more, to make ammonia, NH3.
It sounds energy intensive.
It is, but it's arguably one of the most important industrial processes ever developed. It effectively allows us to feed the world by producing synthetic fertilizers cheaply, supplementing natural sources like guano, which are running out. It literally averted mass starvation. Earned Fritz Haber and Carl Bosch Nobel Prizes, though Haber's legacy is complex due to his work on chemical weapons.
Right. Does nature have a less brutal way?
Oh, absolutely.
Where?
Biological nitrogen fixation. Certain bacteria, often living symbiotically in the root nodules of legumes like peas and beans, have an enzyme called nitrogenase.
An enzyme?
Yes, a complex metallenzyme containing iron, molybdenum, and sulfur atoms. It can take N2 from the air and reduce it all the way to ammonia at room temperature and atmospheric pressure.
Wow, so why aren't we doing that industrial?
Well, it's elegant, but it costs the bacteria a lot of energy in the form of ATP. It's not free, but chemists are definitely inspired by it. There's a lot of research into developing catalysts, often based on metals like molybdenum or iron, that can mimic nitrogenase and activate N2 under milder conditions. Some recent breakthroughs have even achieved direct reduction to ammonia at room temp, which is really exciting.
Mimicking nature. Cool. Section 15.7 revisits nitrides and azides. We covered the basics, but any deeper details?
Just reinforcing the types. Saline nitrides, mainly with lithium and group 2 metals like L3N, covalent ones like BN or P3N5, and those super hard inert interstitial nitrides with D-block metals used as refractory materials. The nitride ion itself, N3, can also act as a ligand, bonding to metal ions and often stabilizing them in unusually high oxidation states.
And diazides, N3 ion.
Yep, linear, isoelectronic with CO2 and N2O. Toxic. Heavy metal azides like leadazide PBN32 are extremely shock sensitive and used as detonators and explosives. Exactly. Ionic ones like sodium azide and N3 used in airbags are more stable, kinetically inert, but still decompose rapidly when initiated, producing that rush of N2 gas. The book even mentions more exotic things like the N5 plus alkation have been made forms incredibly explosive solids.
N5 plus stone sounds unstable. Okay, let's move to hydrides. Section 15.10, ammonia is the big one.
Definitely. All group 15 elements form EH3 hydrides, and yeah, they're all toxic to varying degrees. Ammonia, NH3, from the Haber process, has that pungent smell. Its properties are dominated by hydrogen bonding.
Which explains its high boiling point.
Absolutely. It boils at negative to 33 degrees C, which is much higher than you'd expect compared to phosphine, pH3, or arsane, HH3 below it. That strong hydrogen bonding makes liquid ammonia a fascinating non-aqueous solvent. It can even dissolve alkali metals like sodium or potassium.
Dissolve metals? What does that look like?
You get these intensely colored solutions, usually deep blue. They conduct electricity because the metal atoms release their valence electrons, which become solvated by the ammonia molecules. Really quite strange and useful for certain reactions.
Wow. And ammonium salts?
Ammonium salts like ammonium nitrate or ammonium sulfate behave a lot like alkali metal salts like potassium salts. They're crucial as fertilizers. But ammonium nitrate, as we know, can also be a component in explosives because it decomposes to produce a lot of gas very rapidly.
Right. What about other nitrogen hydrides? Hydrazine?
Hydrazine N2H4. It's a fuming, colorless liquid. Its liquid range is quite wide, similar to water, again suggesting hydrogen bonding is important. Structurally, it adopts a gauche conformation, meaning the two NH2 groups are twisted relative to each other around the NN bond.
And its main use?
Rocket fuel. Hydrazine and its methyl derivatives are very potent rocket propellants. They release a huge amount of energy when they react, usually with an oxidizer like dinitrogen tetroxide. Very efficient thermochemically.
Okay. And the heavier hydrides? Phosphine, arsane, stibane?
pH3, ASH3, SPH3, all highly poisonous gases. Unlike ammonia, they show very little hydrogen bonding between their own molecules. Their main use is in the semiconductor industry for doping silicon or making compounds like gallium arsenide.
And their shapes?
Still pyramidal, like ammonia, but the bond angles get progressively smaller as you go down the group. From about 107 degrees in NH3 down to just over 91 degrees in SPH3. Probably due to less repulsion between bonding pairs as the central atom gets bigger and electronegativity decreases. Their organic derivatives, like triphenylphosphine PPH3, are really important, stable ligands in coordination chemistry.
Got it. Halides next, section 15.1. These elements seem to love halogens.
They certainly form a wide variety. Nitrogen is a bit limited, though. Nitrogen trifluoride, NF3, is the only stable binary nitrogen halide that forms hexagonically. It's pyramidal like ammonia, but it's surprisingly unreactive and not a Lewis base.
Why not a base? It has a lone pair.
It does, but the three highly electronegative fluorine atoms pull so much electron density away from the nitrogen, including the lone pair, that it's just not available to donate. Other nitrogen halides like NCl3, NBr3, Ni3 are known, but they're increasingly unstable and dangerously explosive. Ni3 especially is notoriously touch-sensitive.
Yikes. Okay, what about the heavier elements, trihalides?
EX3 compounds are known for all the heavier elements with all the halogens. They range from gases like PF3 to solids like BF3. Phosphorus trifluoride, PF3, is particularly interesting. It acts as a ligand, bonding to metals, much like carbon monoxide, CO. It's a weak sigma donor, but a strong pi acceptor. Forms complexes like NiPF3-4.
And they're useful chemically.
Oh yes, they're key starting materials for making other compounds. They can act as mild Lewis acids too.
What about pentahalides, EX5?
These are more restricted. Pentafluorides, EF5, are known from phosphorus down to bismuth, but pentachlorides, ECl5, only exist for phosphorus, arsenic, and antimony. Pentabromides, EBr5, only for phosphorus.
The inert pair effect again for bismuth, and something else for arsenic.
Exactly. Bismuth just doesn't readily achieve the +5 state. For arsenic, it's sometimes called the alternation effect. The +5 state is less stable than for phosphorus above it or antimony below it.
What are their structures like?
In the gas phase, they're typically trigonal bipyramidal. But in the solid state, things can change. Solid PCl5, for instance, isn't PCl5 molecules. It's actually an ionic salt. BCl4 plus PCl6, tetrahedral cation, octahedral anion. This packs more efficiently and gives greater lattice stability.
Clever.
Antimony pentafluoride, SBF5, is a very viscous liquid, almost syrupy. In the solid state, it forms a cyclic tetramer with fluorine bridges, showing SBV's strong tendency to be 6-coordinate.
And Lewis acidity.
The pentafluorides of P, A's, and spiri are all strong Lewis acids. SBF5 is one of the strongest known. Mix it with hydrofluoric acid, HF, and you get superacids, capable of protonating things you would normally think of as bases. PCl5 is also a really important lab and industrial reagent for chlorinations and making organophosphorus compounds.
Okay, quick detour. Oxohalides, section 15.12. Oxygen and halogens bonded to the central atom.
Yep. For nitrogen, you get things like nitrosyl halides and nitrohalides NO2X. They're reactive gases, useful as fluorinating and chlorinating agents.
And for phosphorus.
Phosphorus readily forms phosphoryl halides, POX3, like the very common phosphoryl chloride, POCl3, often called POCl3. They're tetrahedral molecules with a very strong PO double bond. PO3 is a gas, POCl3 is a liquid, POBr3 is a solid. They all fume in moist air because they hydrolyze easily.
And uses.
Industrially vital. They're key intermediates for making a huge range of organophosphorus compounds using plasticizers, flame retardants, pesticides, surfactants, all sorts.
Okay, section 15.13 brings us back to nitrogen oxides and oxoanions, but looking deeper at redox properties.
Right, this revisits the complexity. Many accessible oxidation states, plus that kinetic inertness of N2 we talked about, means predicting reactions isn't always straightforward. Thermodynamics might say a reaction should happen, but kinetics might say it's incredibly slow.
How do we visualize stability?
Chemists often use frost diagrams, which plot relative thermodynamic stability versus oxidation state. They visually show things like bismuth V being a very strong oxidizing agent, high up on the diagram wants to go down, consistent with the inert-pair effect, while phosphorus V and phosphoric acid is very stable and a weak oxidant, low down on the diagram.
And the Ostwald process for nitric acid again?
Yeah, it emphasizes that indirect route. N2NH3, Haber neotheto 2NO2 does HNO3. We don't just burn nitrogen in air to get nitric acid directly, because oxidizing N2 is thermodynamically uphill due to that strong triple bond. Reducing it first, then oxidizing the ammonia is actually more feasible overall.
Okay. How strong an oxidizer is nitrate, really?
Moderately strong, but kinetics are key. In dilute acid, nitrate reactions are often slow. In concentrated nitric acid, it's much faster. Why? Because the nitrate ion gets protonated, which weakens the NO bonds and makes reduction easier. The actual reduction product you get, like NO2, NO, or even NH4+, depends on the reducing agent and conditions.
And aqua regia works because of complexation.
Yes. The chloride ions form stable complexes with the oxidized gold ions, OCl4, which pulls the equilibrium over, making the thermodynamically unfavorable oxidation of gold happen.
What about NO2 and nitrous acid?
NO2, in equilibrium with N2O4, is a key component of photochemical smog and acts as an oxidizing agent. In basic solution, it disproportionate. Some gets oxidized to nitrate, NO3, some reduced to nitrite, NO2. Nitric acid, HNO2, is also an oxidizing agent, and its reactions are sped up by acid because it forms the nitrosodium ion, NO plus A, which is a potent electrophile, and Lewis acid.
And NO, nitric oxide.
Its reaction with oxygen to form NO2 is interesting. It's second order with respect to NO. This means the reaction is fast at high NO concentrations, but gets much slower as the NO concentration drops. That's why NO, from car exhausts, persists in the atmosphere for a while. Its concentration is low enough that its oxidation is slow. Catalytic converters aim to reduce NO back to N2 at the source.
And N2O, nitrous oxide.
Laughing gas. Kinetically very unreactive, even though thermodynamically it should be a strong oxidizing agent, it just doesn't like to react.
Okay, shifting down the group. Section 15.14, oxides of P, A's, SB, bi. We expect lower oxidation states to be favored, right?
Absolutely. Phosphorus forms two key oxides, phosphorus V oxide, P4O10, and phosphorus 3 oxide, P4O6. Both have these neat symmetrical cage structures based on a tetrahedron of p atoms.
Can you describe them?
Sure, imagine a p4 tetrahedron. In p4O6, there's an oxygen atom bridging each of the 6 edges of the tetrahedron. In p4O10, you have those same 6 bridging oxygens, plus an extra oxygen atom double bonded to each of the 4 phosphorus atoms pointing outwards. Adding water to these gives phosphoric acid H3PO4 from P4O10 and phosphonic acid H3PO3 from P4O6.
And the heavier elements.
Arsenic, antimony, and bismuth much prefer the +3 oxidation state for their oxides, S2O3, Sp2O3, bi-2O3. In the gas phase, S-con dioxides form molecular cages, S4O6 and Sp4O6, just like P4O6. While S and Seb do form +5 oxides, bismuth dioxide is unstable and hard to characterize, another clear sign of the inert-pair effect stabilizing by fall.
Right. Section 15.15, oxoanions of the heavier elements. This is where phosphate comes in big time.
Indeed. And it highlights phosphorus's distinct redox behavior compared to nitrogen. The common oxoanions are hypophosphite, H2PO2 from Pi, phosphite, HPO32 from PSI, and phosphate, PO43 from PRK.
What's special about hypophosphite and phosphite?
Look closely at their structures. They contain direct pH bonds. This makes them strong and usually fast, reducing agents. Nitrogen oxoanions in similar oxidation states don't have NH bonds. A key application is using hypophosphite to reduce nickel ions down to nickel metal for electrodeless plating, depositing nickel onto surfaces without using an electric current.
And phosphate isn't oxidizing.
Right. Unlike nitrate, which is a moderately strong oxidant, phosphate and phosphoric acid are very poor oxidizing agents. Phosphorus is quite happy in the +5 state.
This ties into arsenic toxicity, doesn't it?
It does. Arsenate, azo-4,3, arsenic V, is chemically similar enough to phosphate that it can sneak into biological pathways that use phosphate. But arsenate is much more easily reduced than phosphate. Inside the cell, it gets reduced to arsenite, arsenic 3. And it's thought that arsenic 3 is the real culprit. It binds strongly to sulfur atoms in proteins and enzymes, messing up their function.
So it mimics phosphate to get in, then gets reduced to do the damage. Nasty. Now, section 15.16, condensed phosphates, linking phosphates together.
Exactly. You can link PO4 tetrahedral units together by sharing oxygen corners, forming POP bridges. This happens when you heat phosphoric acid or phosphate salts driving off water. You can get chains, polyphosphates, or ring cyclophosphates.
It's like diphosphate or triphosphate?
Yep. Heating H3PO4 above 200 degrees C gives diphosphoric acid, H4P2O7, then triphosphoric acid and longer chains. The most commercially important one is sodium tripolyphosphate, Na5P3O10.
The detergent builder.
That's the one. Huge use in laundry detergents, dishwasher powders, etc. It acts as a chelating agent, grabbing hold of Sk2+ and Mg2+ ions from hard water and wrapping them up in a soluble complex. This stops them from precipitating out as soap scum and allows the surfactants to clean effectively. It also helps buffer pH and keep dirt suspended.
Any other uses?
Oh yeah, food industry too. Used in curing hams, processing chicken and seafood to help retain moisture and improve texture.
But there's an environmental downside, eutrophication.
Yes, that's the big one. When large amounts of phosphates from detergents and fertilizers wash into lakes and rivers, they act as nutrients, causing massive overgrowth of algal blooms. When the algae die, their decomposition consumes all the dissolved oxygen in the water, creating dead zones where fish and other aquatic life can't survive. This process is called eutrophication.
So that led to restrictions.
It did. Many countries now restrict or ban phosphates in laundry detergents because of this. Biologically, though, triphosphates are essential. Think adenosine triphosphate, ATP, the universal energy currency molecule in all living cells. It's based on that triphosphate linkage.
Amazing link between washing powder and life itself. Okay, nearly there. Section 15.1 seeds phosphazines, swapping oxygen for nitrogen.
Precisely. This is where phosphorus-nitrogen chemistry really gets interesting. Phosphazines are polymers and rings containing repeating R2PN units. The key analogy here is with siloxanes, silicones, which have R2SiO units.
So they're like silicones but with P and N.
Structurally analogous, yeah. And that analogy helps understand their properties, like high flexibility. Important starting materials are the cyclic phosphazine dichlorides, like the trimer, Cl2PN3, or tetramer, Cl2PN4. They're made from reacting PCl5 with ammonium chloride.
Then you can modify them.
Easily. Those chlorine atoms are readily substituted by all sorts of other groups, like alkoxy amino alkyl groups, which allows chemists to tailor the properties of the resulting polymers, the polyphosphazines.
What kind of properties?
Well, many polyphosphazines are very flexible, remaining rubbery down to low temperatures, similar to silicone rubbers. But the really exciting area is biomedical applications.
Why are they good for that?
Because many of them are biodegradable. They break down slowly in the body into harmless products like phosphate and ammonia. And by changing the side groups, the R groups, you can control their properties, make them hydrophobic or hydrophilic, control the degradation rate, make them bioinert or bioactive.
So custom materials for inside the body.
Exactly. They're being developed as bioinert housings for implants, as structural materials for artificial heart valves or blood vessels. Some types can bond to calcium ions and act as scaffolds for bone regeneration. The polymer degrades as new bone grows in.
And drug delivery.
Huge potential there, too. You can trap drug molecules within the polymer matrix, or even attach them directly to the polymer backbone. As the polymer slowly degrades, the drug is released over a controlled period. People are developing systems for delivering chemotherapy drugs like cisplatin, neurotransmitters like dopamine, steroids. It's a very active research area.
That sounds incredibly promising. Finally, Section 15.18, organometallic compounds of as, seb, bi, bonds directly to carbon.
Yep, metal-carbon bonds involving these heavier group 15 elements. We see compounds in both the +3 and +5 oxidation states.
What about +3?
Examples are things like trimethylarsine, SE3, or triphenylarsine, SVH3, usually made using Grignard or organolithium reagents. Stability generally decreases down the group, as SIDS bi. And aryl compounds with phenyl rings tend to be more stable than alkyl ones.
Are they bases?
Yes, they all act as Lewis bases, donating their lone pair to form complexes with metal ions, especially D-block metals. They're considered soft ligands. Basicity also decreases down the group. As Seb-B, arsenic can even form chains or rings of hetem. As atoms bonded to organic groups catenated compounds like cyclic Astis5, Me5.
Can they form double bonds to carbon?
They can. You can get heterocyclic rings analogous to benzene, like arsobenzene, C5H5As, which is surprisingly stable, or stibabenzene, C5H5Sb, which is much less stable and tends to polymerize.
And the +5 oxidation state?
You can make things like tetraalkylarsonium salts, SO4 plus Br, by reacting a trialtylarsane with an alkyl halide. The tetraphenylarsonium ion, As2,4 plus SOO, is a common bulky cation used in inorganic chemistry to help crystallize large anions. Pentaphenyl arsenic, SMSO5, exists and has a trigonal bipyramidal structure. Interestingly, while its antimony analog, SBPH5, adopts a square pyramidal geometry.
Any uses for these organometallics?
Historically, organoarsenic compounds were used as pesticides, like Paris green, and even pharmaceuticals, like Salvarsan for syphilis, but their high toxicity means they're used much less now.
Wow, what a journey through Group 15. From essential nitrogen and phosphorus to toxic arsenic, simple gases to complex biomedical polymers.
It really covers a huge range, doesn't it? We've seen their different physical forms, the allotropes, the massive variety of compounds, nitrides, azides, oxides, hydrides, halides, oxalanions, and that wide spectrum of oxidation states, governed by things like electronegativity and the inert-pair effect.
Plus their huge industrial impact, fertilizers, explosives, semiconductors, detergents, and their absolutely critical roles in biology, from the nitrogen cycle and DNA to ATP energy.
And we even saw how that phosphorus-nitrogen chemistry and phosphazines is leading to cutting-edge materials for medicine. It shows that the chemistry of these elements is far from static. There's constant innovation.
So what does this all mean for you, the listener?
Well, hopefully, it shows that understanding these seemingly unrelated elements actually reveals some fundamental chemical principles. Structure dictates function. Kinetics versus thermodynamics, the importance of bonding, like hydrogen bonding. And it connects that fundamental chemistry directly to the real world, from feeding the planet to designing new medical treatments.
We really hope this deep dive has given you plenty to think about and maybe sparked some new curiosity about the pnictogens. They're certainly more interesting than just a column on the periodic table.
Absolutely. Thanks for joining us on this exploration.
And a warm thank you from the whole Last Minute Lecture team. Until next time.